Welcome back to AI Peer Review. This is where we really get into the weeds on the research that's pushing AI forward. And today we're tackling, well, probably the biggest headache for large language models, that long context bottleneck.
Yeah, it's a thing that makes everything slow down, right? It gets super expensive computationally when you try to feed in lots of text. But there's this really interesting paper, DeepSeek-OCR, Context's Optical Compression. And it takes a pretty radical swing at the problem.
Radical how?
Well, instead of thinking about documents just as text, streams of tokens, it asks, why not use an image of the document? Use the visual modality itself as a way to, compress all that text information really densely.
Okay, that's a different way to think about it. Using vision as a compression layer for text.
Yeah.
So our mission today is really to see if this optical compression idea holds water. Like, how much text can you actually cram into an image format? And crucially, can the model get that text back out accurately? That's the big test, right?
Exactly. Is it feasible?
So let's set the stage. We all know the attention mechanism in transformers is powerful, but it's also why costs scale quadratically. Double the text, quadruple the compute. Trying to process something book length, forget it unless you have a, massive pile of GPUs.
That's the crux of it. And the insight from DeepSeek-OCR is, well, it's kind of about geometry, really, and efficiency. Think about a high-res image of a page. It's packed with info. And representing that image might take way fewer vision tokens than the thousands of text tokens the page actually contains.
Fewer vision tokens than text tokens.
Okay.
How much fewer are we talking?
The paper, the abstract, throws out numbers like potentially up to 20 times compression.
Wow, okay, 20 times. That's huge. If the accuracy holds up. So you're turning a vision language model, a VLM, into this kind of compression and decompression engine, a way to game the sequence length limit. What are the main parts that make this work?
It basically boils down to two key components, both really optimized. First, you've got the deep encoder. That's the new bit doing the visual compression, turning the page image into this compact token embedding. And second, there's the decoder, the DeepSeek 3B MoA 570M. Its job is to take those compressed vision tokens and, reconstruct the original text and do it efficiently.
Right, the decoder, DeepSeek 3B MoA. That name suggests mixture of experts, which usually means efficiency gains at inference time. It sounds big, 3 billion parameters, but maybe it's not.
Exactly. It is frugal. It uses that mixture of experts approach. So think of it like this. It has the knowledge base, the capacity of a pretty large 3 billion parameter model. But when it actually runs, when it does the decoding, it only activates a small subset of those experts. Specifically, it's like 6 out of 64 specialist experts plus 2 shared ones, so the actual compute cost. It's much closer to maybe a 500 million parameter model. Tiny, relatively speaking.
So you get the big model smarts.
At the small model cost, yeah. Best of both worlds for the decoding part.
Okay, so decoding is efficient. But the encoding, that seems like the real mountain to climb here. The deep encoder. Vision models, especially high-res ones, can really chew up memory with global attention. How do they design this deep encoder to hit their goals? Handle high resolution, but keep the activation, the memory usage, low.
Yeah, that's the core innovation. The design is actually pretty clever, really focused on that memory issue. What they did was connect two existing powerful models in sequence, serially. The front bit is based on SAM-base, segment, anything model. Great for visual perception, picking out parts of the image. And the back end is based on CLIP large. That brings in the depper visual understanding, the knowledge.
Okay, but CLIP. CLIP uses dense global attention, right? That's usually the Marriott, especially with big images like document pages.
Yes, precisely. And that's where the star player comes in. They stick this 16x convolutional compressor right in the middle, strategically placed.
A compressor, tell me how that works.
Okay, so follow the data. You get an image, say 724 by 124 pixels. It goes into the SAM part first. That part breaks it down into 4096 little patch tokens.
Okay, 4096 tokens representing image patches.
Right. And since this first stage uses window attention only within local areas the memory cost is manageable, it's okay. But then, if you just fed all 4096 of those tokens straight into the CLIP layer's global attention, boom, memory overload.
Yeah, that wouldn't work.
It wouldn't. So before those tokens hit that expensive global attention in CLIP, they pass through this convolutional compressor, and it just drastically cuts them down from 4096 all the way down to just 256 tokens.
Wow, okay. A 16-fold reduction right there.
Exactly. The compressor is basically figuring out, okay, what are the most important 256 visual pieces here, and passes only those along. That single step keeps the memory footprint totally under control, even when you're looking at a full high-res document.
That's a really smart architectural choice. Just compress before the expensive part. And I
Mhm.
saw they also built in different resolution modes, like tiny, small, base, large, to kind of tune this compression.
Yeah, absolutely. They needed that flexibility. You can see it in Table 1 in the paper. Modes go from tiny 512 by 512 input, giving just 64 vision tokens, all the way up to large 1280 by 1280, giving 400 tokens. And then for really crazy stuff like super dense newspaper pages, they have these dynamic modes, like one they call Gundam. It uses tiling, kind of stitching pieces together to handle ultra high resolutions without blowing up memory.
Okay, the architecture sounds solid, really clever design. But does it work? Like when they actually tried to get the text back out, they used something called the Fox benchmark for this, right? Measuring the OCR precision versus how much they compressed it.
They did. And the results, if you look at Figure 1A and Table 2, they really back up the idea. It turns out there's a sort of sweet spot. When the compression ratio is, say, around 10x or less, the decoding is almost perfect, near lossless.
Give me some numbers. What does near lossless look like?
Okay, so take a document chunk that normally has, let's say, 600 to 700 text tokens. They compress that down into just 64 vision tokens. That's about a 10.5x ratio.
Wow.
And the precision they get back, 96.5%.
96.5% is really, really good. That means almost all the original text is recoverable from just those 64 vision tokens.
Exactly. It shows that the core information is preserved in that compressed visual form, at least up to that point.
Okay, but they were aiming for 20x compression too. What happens when you push it further? If you're squashing, I don't know, a couple thousand words into those same 64 tokens, does it just fall apart? Where's the limit?
Right, you have to find a breaking point. And performance does drop off past that roughly 10x mark. Makes sense. But it's surprisingly resilient. Even when they push the ratio towards 20x, like cramming 1,200 or 1,300 text tokens into 64 vision tokens, the accuracy is still around 60%.
60%. Okay, maybe not good enough for, like, legal documents.
Probably not for critical stuff, no. But the fact that you can still get 60% accuracy back from such an incredibly compressed, almost blurred representation, that's actually pretty profound. It really validates optical compression as a viable strategy for managing context, even if it becomes lossy at the extremes.
All right, so it's feasible, even if there are trade-offs by compression. Let's talk practical use cases. They tested this on the doc bench, which is more about real-world document understanding. And there, it's all about token efficiency, right?
Exactly. This is where you see the payoff in practice. Check out Figure 1B and Table 3, looking at edit distance, how many changes you need to make the OCR output match the original. DeepSeek-OCR, even the small version, using just 100 vision tokens per page. It actually beats established models like DeepSeek-OCR 2.0. And DeepSeek-OCR 2.0 needs 256 tokens per page to get similar results.
So right away, that's like a 2.5x token saving.
Yeah.
Pretty significant.
It is, and then when you get to the really long, complex documents, the whole reason for this approach.
That means it gets even bigger.
Massively bigger. Take those multi-column monsters. DeepSeek-OCR, using its high-res Gundam mode, might use, say, fewer than 800 vision tokens for a whole page. And it outperforms models like MinerU 2.0, which the paper says can need almost 7,000 vision tokens on average for the same kind of page.
7,000. Okay, so 800 versus 7,000. That's nearly a 10x efficiency gain right there for the really tough stuff.
Exactly. A huge win for parsing those giant documents.
Now, I saw in Table 4, it looks like you have to pick the right mode, the right compression level for the document type.
Yes, and that ties back perfectly to that compression boundary we talked about. If you have something like slides or maybe book pages, which don't have that many words per page, maybe under 1,000 text tokens, you can use the smaller modes. 64 or 100 vision tokens, because the compression ratio stays comfortably below 10x and you get great results.
Makes sense.
But then you hit something like a dense newspaper page, maybe 4,000, 5,000 text tokens packed in there. For those, you absolutely need the higher fidelity Gundam modes. You need more vision tokens to capture all that detail accurately because you're pushing that compression limit otherwise.
So you dial the number of vision tokens up or down based on the density of the source text. Now, they also talked about deep parsing, going beyond just getting the text out.
Yeah.
What else can this system do?
Right. This is what they call OCR 2.0. Because it's end-to-end and the MOE decoder is pretty powerful, it can understand structure, not just characters. So look at Figure 7, for instance. It can see a chart in an image like a bar graph and actually output that data as an HTML table, programmatically usable.
Okay, that's cool. Structure extraction.
Yeah, or look at Figure 9, chemical formulas. It can read those complex diagrams and output them in SMILES format, which chemists use. Figure 10 even shows it parsing simple geometric shapes using something called slow perception encoding. Lines, angles, basic stuff. It's all handled within the same model.
And it's multilingual, too. You mentioned nearly 100 languages.
That's right. They built a massive data engine, scraped something like 30 million diverse PDF. So it's not just English. It handles documents in many, many languages. Makes it very robust for real-world data.
And the scale. This isn't just a lab experiment. They talk about production capability. How fast can this thing generate training data?
The numbers are pretty staggering. On one decent GPU, an A140G, they can process over 200,000 pages a day. Scale that up to a small cluster, say 20 nodes. You're looking at generating training data at a rate of 33 million pages per day.
33 million. Okay, that completely changes the economics of creating training data sets for future models.
Absolutely. It lowers the barrier significantly.
Okay, let's step back and think bigger picture. This whole vision text compression thing.
Yeah.
It's fundamentally a way to manage context, right? A controlled, lossy compression. What does this tell us about how we might build future AI systems that need truly massive context windows?
Well, if you connect the dots, especially looking at their discussion around Figure 13, this mechanism, it provides a really interesting parallel to how human memory seems to work. Specifically, memory forgetting.
Forgetting? How so?
Think about it. Our memories aren't perfect recordings, right? Especially older memories. They tend to get fuzzier, less detailed over time. We compress them, keep the gist, lose some specifics. It's a natural way to save cognitive resources.
Okay, so you're saying this optical compression, dialing the resolution up or down, is like a machine simulating that.
Exactly. You can treat context like memory. Stuff you just saw, recent context, you need it sharp. So you use high resolution, low compression, lots of vision tokens, keep it crystal clear. But for older context, stuff from way back, maybe you don't need every single detail perfectly preserved. So you can progressively downsample its visual representation, go from large mode to small, maybe even tiny, reduce the vision tokens.
Intentionally blurring the older memories, making them lossy to save compute.
Precisely. You're making an explicit trade-off. Memory fidelity versus computational cost. And by managing that trade-off intelligently, keeping recent stuff sharp, letting older stuff fade slightly, you could potentially build architectures with, well, theoretically unlimited context. You're not bound by having to store every single token perfectly forever. You manage the fidelity of the representation based on its age or relevance.
That's actually a really powerful concept. Shifting from perfect recall to managed fidelity. It feels like a much more scalable approach.
It definitely seems like a promising direction, particularly for tasks involving long documents or needing long-term memory. This optical compression gives us a new tool, a new knob to turn.
So wrapping up, the key takeaway here seems clear. DeepSeek-OCR demonstrates pretty convincingly that this optical compression idea works. It can give you anywhere from, say, a 7x to maybe even a 20x reduction in the number of tokens needed to represent context, depending on the fidelity you need. And that could fundamentally change how we approach building VLMs for document processing and long context tasks.
It really could. Which leads me to a final thought, something for you, the listener, to chew on. We've seen this works really well for statting documents, right? Images of pages. But what if you applied a similar visual compression idea to dialogue history? Think about long-running AI agents, chatbots that need to remember conversations from hours, days, even weeks ago.
Compressing the chat history visually.
Yeah. After a certain point, maybe beyond the last K turns, could you start rendering older parts of the conversation as images and compressing those? Could you get that same kind of, say, 10x efficiency gain for conversational memory? Allowing an agent to effectively remember vastly more context without hitting that token limit wall. What would that enable?
That's a fascinating extension, turning chat logs into compressed visual memories. Definitely something to think about. On that note, thank you for joining us for this AI peer review. We'll catch you on the next deep dive.